This diagram shows a strange mathematical impossibility. You put exactly 159 liters of raw crude oil into a refinery, but somehow you get 170 liters of usable product out. Every single day, over 100 million barrels of crude oil undergo this specific expansion, scaling a single chemical anomaly into a massive global surplus. This volume gain is a calculated chemical mutation, a highly engineered method of restructuring molecules that makes oil refining exceptionally profitable. To understand how we artificially inflate our global energy supply, we have to follow this thick black liquid from the crushing pressures of the ocean floor straight into the fires of a distillation tower. The journey starts 12,000 feet beneath the ocean surface. Here, ancient sediments have decomposed, trapped under millions of tons of rock and water. Reaching it requires colossal machinery and heavy physical labor.
Crews work 12-hour shifts connecting massive steel drill strings, manually handling heavy pipes end to end to pierce distances roughly 12 times the height of the Eiffel Tower. If a crew miscalculates the pressure inside that reservoir, the crude can surge upward entirely out of control. This sudden release triggers a massive blowout, leading to devastating environmental damage and billion-dollar cleanup efforts. To defend against that, engineers install a massive steel block on the seabed called a blowout preventer, or BOP. This diagram illustrates how it acts as a giant emergency valve. If pressure spikes, it clamps tightly around the drill pipe, containing forces exceeding 10,000 psi. Once the well is secured, the natural subterranean pressure pushes the resources up. But it isn't pure oil. What rises through the subsea network is a raw, turbulent mixture of crude, natural gas, water, and fine sand.
Every phase of offshore extraction is a constant battle against extreme forces. We fight the crushing weight of the ocean above and explosive reservoir pressure from below, pulling a raw slurry to the surface. That rising slurry is captured by floating fortresses, known as FPSOs, floating production, storage, and offloading units. These massive, anchored structures sway above the trenches to capture the raw flow. Before the crude goes anywhere, the FPSO acts as a preliminary sorting facility. It strips away the natural gas and ocean water, storing up to 2 million barrels of the traded oil right inside its hull. Once the FPSO reaches capacity, it offloads its cargo onto specialized intercontinental tankers. These colossal vessels, dwarfing the assist tugboats, haul the crude across the oceans toward dry land. Billions are poured into subsea robots, into deepwater wells, and floating storage hubs, all to keep a continuous, uninterrupted flow of crude oil feeding into terrestrial refineries. When the crude oil arrives at a refinery, it's pumped into a furnace and blasted to around 650 degrees Fahrenheit. The liquid vaporizes and is directed into towering metallic columns. This map details a process called fractional distillation. The column separates the vapor by exploiting different boiling points across a strict temperature gradient. It is extremely hot at the base, roughly 400 degrees Celsius, and gradually cools to around 50 degrees near the top. Inside the tower are dozens of levels, or trays, lined with a bubble cap design. These mushroom-shaped fittings force the rising, superheated vapor to physically pass through a pool of cooler liquid sitting on the tray. Heavy hydrocarbons have higher boiling points, so they condense into a liquid and get trapped in the lower, hotter trays. The lighter molecules escape the liquid pool as a gas, continuing their climb to the cooler trays above. While gasoline and diesel separate out cleanly, standard distillation leaves behind a dense, heavy residue at the bottom. If you tried to boil this thick sludge at normal atmospheric pressure, the molecules would just crack apart and burn. The entire column is a giant physical sieve. It operates entirely on the laws of thermodynamics, sorting ancient molecules purely by their tolerance for heat. To safely extract value from that heavy bottom sludge, engineers drop the pressure inside a second column using a steam ejector. This process, called vacuum distillation, allows the thick residue to boil at a much lower temperature without destroying the chemical bonds. Once separated, these heavier components undergo catalytic cracking. We expose the dense hydrocarbon chains to extreme heat and chemical catalysts, snapping them apart into the smaller, lighter molecules that make high-octane fuels. This chart explains the math paradox from earlier. When you take dense, heavy molecules and crack them into lighter ones, they physically take up more space. A 159-liter barrel of crude expands into 170 liters of finished products like gasoline, diesel, and jet fuel.
This volume expansion is known as processing gain. For refiners handling millions of barrels daily, that extra 11 liters per barrel translates into continuous profit, ensuring literally no drop of the resource goes to waste. Refining crude oil is an artificial mutation of matter. We extract a finite resource from the earth and chemically restructure it to maximize every possible ounce of human utility. This refined black liquid drives global trade, creates the plastics in our homes, and fuels the political and economic obsession with constant extraction to keep our global markets stable. But as clean energy technologies steadily rise, we have to ask how much longer this ancient resource will hold its grip on modern civilization. We have proven we can build deep-sea fortresses and manipulate molecular chemistry to power the globe. Human ingenuity now faces a choice: continue optimizing extraction, or use that same engineering brilliance to transition our global infrastructure to renewable power.